Yeah, okay. So now I started. So yeah, so the so anyway, like these parts were from the previous class. So challenge number one, how do you take the gradient? Challenge number two, how do you deal with the vanishing and exploding gradient? Okay, so I have not mentioned exploding gradient here, but I have now mentioned. So the same problem can happen here. It could be like 10 to the 8, it could be another 10 to the 7 and something like that. So, but if I multiply out, then it will be 10 to the 20 or something, and then it will go into overflow mode. So these are the problems when you are dealing with deep neural networks. So imagine you have many layers, hundreds of layers multiplying very small numbers hundreds of times, then you easily will go below 10 to the minus 16. Okay, and then there are cases where you have the network itself has to be long because the problems, I mean, has to be long. Is not a correct statement, like, because there are now in modern networks that doesn't have to be like that. So they so-called recurrent neural networks, and these networks are for problems on sequences. Okay, so for instance, if I want to translate a sequence of English words to a sequence of French words, so it's a sequence problem. So the network can get very long depending on the input sequences and so on. So they are inherently very deep. Okay, so how long will be the time steps and so on, depending on that, they can become very long. So there are issues like that in RNN, and then people came up with slightly modified variants which are called LSTMs, where they exactly try to deal with this exploding gradient and so on, because the idea was that in RNN there is some concept of memory, and then you don't put weights along the memory so that the memory doesn't get corrupted when it's going through the time sequence. So these were the things they tried to deal with in LSTM, and then now there are even more powerful methods like attention-based methods, where where you try to not just keep an emphasis on the very recent sequence that you have seen, but rather you put attention, so-called attention, on also on previous words on the sequence, and then internally also there are some attention mechanism and so on. So um, there are ways that people have tried to deal with these cases. So we will try to see if we have time to deal with this and discuss this RNN and remaining part. So another challenge that we have is non-smooth objective. So if I start using activation functions that are not smooth, for instance, if I use ReLU, then it's non-smooth, and again we have a problem of how do I compute gradients for a non-smooth function, because to use a stochastic gradient method, I do need gradient, right? So these are the challenges. Now, the first challenge is to compute the gradient. And if I consider a linear chain network, the linear chain network looks like this. Is a very simple case where I have an input x1, and then it goes to another node. So I take a linear combination. So it's x1 w11. So I get a11. If I do a so after activation, I do get a11, and then I pass on, and then I do a linear combination again. So again, I do a linear combination here again with h11 and w12, and then I get a21 and so on. So I keep doing this. It's just that it's a linear network, may not be very powerful, but just to see, even for a simple linear network, what are the ways to compute the gradient? Because we want to compute the derivative. So what we will see here is this is how it will look like if I want to compute the derivative. So I see my loss function as weights. Remember that sometimes I use W, sometimes I use theta for weights. In this case, I am using theta. So overall, my loss function is a function of theta. Okay, so by this logic, I will be in a problem. So let me write it W here, because the weights are indeed using W here. Okay, so I made a mistake here. It should be W here. Okay, so this is a loss function of W. Let us say W. Okay. So here in W, we collect all the W. Okay, so in this case, like, W is a vector of unknowns, which are W11, W12, and W13. Okay, so I've collected them all, and if I have to compute the gradient, then my loss function, the gradient of my loss function. This is with respect to this will be del L by del W1, del L by del W2, and del L by del W3. Okay, so this is the values that you want. So first, let us focus on del L by del W11. Okay, so this is the weight variable. So we have to compute the derivative with respect to this. So what will happen in this case is that we will see the loss as a so we will see the loss as a function of all these intermediate variables as well. Okay, so that's the point. So how does it look like? Well, I see loss, so I have to reach here, right? So I have to take derivative of the loss with respect to W1. So how do I reach here? I reach here by looking at this chain. Okay, so I have to look at this chain like this. Okay, so let us see how it looks like here. So first I see loss as a function of y hat. Okay, so then I compute a gradient a derivative, partial derivative with y hat. Now I see y hat as a function of okay, did I not do a mistake here? So then I do y hat as a function of a31. Okay, okay, so there will be some mistakes here. So y hat as a31. Okay, and a31. Okay, so y hat as a31 and a31 as a function of h21, h21 as a function of a21, e21 as a function of h11, and h11 as a function of a11, and a11 finally have a dependency on w11. Okay, so this is how we have seen. Okay, so y hat as a function of a31, e31 as a function of h21, h21 as a function of a21. Okay, yeah, it's a21, and a21 as a function of h11, h11 as a function of a11, and a11 contains w111, right? Okay, but okay, yeah, I mean, according to our notation, this will be just a w11. Okay, so it's a w11. So this is how we see the network, and that is why we have expression like this. Okay, so this is an example of a linear network, and that's how you have computed the gradient with W1. Okay, if you want to compute gradient with respect to W12, so if you are going to do del L by del W12, then you will stop at A21 basically here. Okay, you will stop at A21 and then A21 by, so in this case will be L theta W. So it's W by del y hat, and del y hat as a function of del A31 and A31 as a function of h21 and del h21 as a function of a21, and then finally a21 was formed from W11. So del A21 by del W12. Okay, this is what I wanted. So then hence I stopped here. Okay, so this is how I see the so for the deeper weights, I have the chain is longer, and for this weight the chain is not that longer, and then if you have to do this, you will stop right here. Okay, and you will do del A31 by del 13. So this is the this is how the derivatives are taken, and this is a very simple network, and then the chains can be long. And now we will see today how we will do it for multi-layered network with multiple nodes as well. Okay, so that is, we have used the chain rule. Chain rule can be computed in blocks as follows. Remember that in the chain rule, I mean, I could see dependencies, I may not see direct dependency also. I may see dependency also like this. It doesn't matter, okay? I could have written a del y hat by del a to 1, okay? If I know these values, then I can even jump it, okay, and take these values. But there is a reason behind doing this. It's because these intermediate values will be known to us. So all these intermediate values will be known to us. So that's why using these intermediate values, we can actually arrive at the derivative with respect to the weights we are looking for. And these intermediate values are available thanks to the feed forward network that we have. So since during the feed forward, you go via this way, and then you have these intermediate values are known. Okay, and based on those intermediate values, it's possible to calculate these values. Okay, I will come back to this later if you're not sure about this. I will discuss this in full detail. Okay, so chain rule can be computed in blocks. Chain rule can be computed in blocks as follows. Okay, there is nothing here. Okay, I don't know. Okay, so let us see in the multi-layer network here. So you have input units. You have hidden units. So these are called hidden units. This including this, and this is the output. These are the output units. Okay, so these guys are called units. Okay, so these guys are all called units. So these are hidden because these are the innermost layers. So a directed network with a set of inputs and outputs. So directed because I'm mostly going always this way. So there are no loops also. Inputs are just inputs units. So they are basically the sample features only. The input units are basically, these are just the data values, and no neurons are here in the input unit. So these are not neurons. Okay, the neurons are actually here. This is where you are computing the linear combination and activation. Here there is just data here. Okay, so xn and so on. Outputs are called output units. So these are the output units. Okay. Intermediate units are the hidden units. The network is called layered because there are many layers. Okay. So these are the layers of the network. Input is input layer, output is output layer, intermediate layer are hidden layer. Deep network is a network with many hidden layers. Okay, so the we call a network a deep network when you have many hidden layers. Fully connected network is the network in which each node is in the previous layer is connected to each other node is the next. So this is the example of a fully connected layer because each node here is connected to each of the node in the next layer. Okay, so that's an example of a fully connected layer. Edges of the network graph are weighted. So edges of this network are weighted. So you have some weights on them. Okay, so if we zoom into some of the units or the neurons, then this is the familiar perceptron. Okay, so perceptrons we have seen before. So these are nothing but the perceptron, and inside this we are doing this linear combination and activation. For example, if I look at this, then the inputs are coming from all this. Okay, so inputs are coming from all this. I will take a linear combination of these input values, and then the weights are here. So these are the weights of the edges, and then I will take a linear combination of this. So you can treat this as some intermediate x1 value, x2 value, x3 value, and so on. You take a linear combination. So this is the example of a linear combination. And then finally you do an activation. Okay, so this could be the sigmoid and or many. So this is like sigmoid, and then you have a soft plus, and then ReLU and so on. So there are various ways that I can do the activation. So one neuron is a one perceptron. Okay, that's what so individual neurons operate on a set of inputs and produce a single output. For example, a single neuron may do this. So this is what we have explained here. So we have done a linear combination that is generated by plus, and then we have done a final activation by F. So here the parameters of the network we know are the weights and then the biases. Okay, so this is the bias term here. We just take one also as a input, and then multiplied with weight, and that will become the bias that we are looking for. So bias is also a weight of your network that is supposed to be found. So that is F is a function of the input sample and the weight. So if we think of the network, then as I said before, depending on what I'm trying to do, I can see this as these are the parameters that are involved in my network. So the samples and then the weights of the network. So if I am training, then the samples are known to me. So that then I see this as a function of weights, and then trying to minimize the function value for the weights. And if I'm doing the testing, then the weights are already determined during the training, and then during testing it becomes a function of the x1 to xn. Okay, so earlier I have told you that there are many options of choosing activation functions. So for example, this is the continuous case, and this is also the continuous case, which is the tanh. So these are just a plot of the tanh function itself. And then we have slightly different variants of this. So these are called ReLU activation functions, which are clearly discontinuous here. And then you can have some continuous analog of that. Okay, so which is the blue curve here. So this is like the soft plus activation function. And as we know, we need the derivative. So here in the column, right column, we are given the derivatives of these activation functions. Earlier we said that this is non-differentiable. So non-differentiable at z equal to 0. But what we can do is that we can define some derivative at 0 as well. So at 0 we define it to be 1. Okay, so by convention, okay, we can say that at 0 we take it as 1, and then the remaining places the derivative is 0 anyway. So at the problematic part where z is equal to 0, we can define the derivative to be 1. Okay, so in the other cases it doesn't matter. Other cases derivatives are found in closed form, so there is no issue here. And the reason why we need to know the derivative of the activation function is because we need to compute the gradient of the loss with respect to the intermediate values, and these are the ones that will appear in the chain rule. Okay. So we can also have vector activation. So we can have neurons that have multiple coupled outputs. So one neuron can actually produce multiple output as well. Okay. So after activation, we may have a multiple output. Okay. So in this case, the function operates on a set of input to produce a set of outputs. Okay, and modifying the single parameter in W will still affect all the outputs, obviously. So example of vector activation is so-called softmax. So in the softmax, what you have is the output after that activation function is y1 to yl. If we go back and see the other previous activation function, they are real valued. Okay, so this is 1 by 1 plus exponential of z. Okay, so the output is real here. Okay, so this is single output activation function, but what we are talking about now is the vector output. Okay, so this is a kind of activation function that is producing vector output. So softmax in particular is defined like this. So I can define the zi as wij, xj, bi, and then so for each zi, let us say this is yi, then yi can be computed as exponential of zi divided by the sum of the exponential of zi. Okay, so this is just something one has to memorize. So how can I produce multiple output? Then so you take a linear combination and so on, and then you do exponential of zi to compute the yi output, exponential zi divided by the sum of all the exponential of these z values. So there are cases where we may want multiple output. Okay, so in a multi-class case, right? So yeah, so in this case the parameters are w, j, I, and b, obviously. So yeah, and these are the parameters we are supposed to learn. Okay, so what are the notations for the neural network? I have defined before, but again, in a deep neural networks, we have like multiple layers, and then we need to define weight vectors like this. So this is something I have also explained before. So W superscript 1 denotes the weights between the input layer and then the first hidden layer, and then the weight superscript 2 means the weights between the first hidden layer and the second hidden layer, and so on. Okay, and the subscript denotes the edge between ith unit of the previous layer to jth unit of the current layer. Okay, so these are the things, and outputs are usually denoted by y1 to yl. So input layer is the zeroth layer, obviously denote the output of the ith perceptron like this. Okay, and so input to the neuron according. So we can also define, since we are using all these y all the time, and then output we denote like this. The input also we could have defined as y0, right? So y0. So that's what we are trying to say here. So just to keep the consistent thing during the algorithm implementation, we may want to keep choose y0 as the input. Okay, and then this is the first output, second output, third layer output, and then the final output. It does not have any superscript at all. It's just the output is plain yi to yl. Okay, so these are the notations. I think it's clear to us. And what is and the training set are given like this. So there is a slight change, slight remark here for the notation itself is like now we are taking the label data as x1 d1 instead of x1 y1. Okay, so d here stands for the desired. Okay, you can remember like this desired label. So first input desired output is d1, second input desired output d2, and so on. So this is the notation we will use throughout this lecture. So our label data is this, and the sample xn can have so many components, and dun can also have like so many components. Okay, and yn can be a vector, is the nth vector of the actual outputs of the network, and we will sometimes drop the first subscript when referring to a specific instant. Okay, we will sometimes drop the subscript like this one, first subscript n here. Okay, so these are the notations. Inputs are encoded as vector of numbers. So inputs, as you know, if you are modeling a problem, it could be in variety of shapes, variety of forms. If you are working with images, then they will be pixel values. If you are working with speech processing, then there will be some speech data. And if you're working with text, then it will be text data, and so on. Okay, and depending on how you encode it, if you are working in training a game, then it will be let us say the states of the game, and then the rewards you get, and so on. So that's how you can create the label data. And if the output is real valued, then nothing special is required. But if the output is vector valued, then the notations for us will be like this. The D is the vector value, so obviously it has k components here. Okay, so for a multi-class classifier, what we use is a softmax, like I have discussed before. So I go directly to this here. So multi-class classifier, you will usually use the softmax. Okay, so in other words, like you have to make a, so it's like a given image, then you have to identify among 10 animals, let us say. So whether it's a cat, dog, elephant, giraffe, tiger, okay, lion, whatever. So you may want to produce so many outputs. Okay, so in those cases, we may use this multi-class classifier. Okay, I will skip few things which are not that important for us from optimization point of view. So in other words, like the training data may look like this, which is a set of pixels. So this will be some matrix of pixels. Okay, so if you are doing handwritten digit recognition, then it will be some matrix of pixel values. Okay, so it's a grayscale, so it will be some number indicating how black the pixel is. Okay, so in this case, the training data will look like, so pixel data. So this is your X, okay, and these are your labels, label D. Okay, so X sample 1 is the pixel data which corresponds to 5, and this will be a matrix of value. You can also linearize, it doesn't matter. Okay, I'm sorry, why? I'm sorry, something happened here. Okay, so something bad happened. Okay, so here you may have xi, which is the pixel data corresponding to 5, and then this is yi. Okay, so yi. So these are the corresponding levels. So this is how we have the training data that looks like. And yeah, of course, so we define a loss function like this. Also, there is a slight change in my notation. Now I am, instead of loss, I am using a word which is stands for divergence, like how diverging is the prediction from the actual level. So I will use div, okay, instead of the loss. The same thing stands for the same thing. So I can define some divergence function here to calculate how far I am from the desired loss. So these are the like the outputs, okay, and then I will find out how different the outputs are from the desired output. So this loss function takes takes the predictions, which is here in this case f xi w. So this is the output from the network, and this is the desired output, and based on that we build a divergence function from here. Okay, so okay, I think this part is going a bit outside. Okay, so the loss, one very simple loss function would be L2 divergence, which is nothing but the norm of y minus d. Okay, so y is this this output here. So one simple loss function would be y component wise subtraction. So this is like y1, this is y2, and then you subtract y1 minus d1, y2 minus d2, and so on, and then you square it and so on. Good thing about this loss is that it's differentiable. So if I do del div by del so del div by del y, then it's differentiable. Okay, it's a square of a function, so it's easy to differentiate this. So yeah, so and then sometimes like one may use some other kind of divergence functions, is like so-called KL divergence and so on. Okay, so this is another loss where, let us say, if you have a binary classifiers where we want to only check whether something is present or not present. Okay, so this is a case where you have binary, either it's yes it's or no. Okay, so in this case one may use so-called cross entropy loss. So you may memorize like this loss is like this. Okay, so for the optimizer point of view, you have many options. You may define loss to be like this. Well, many in the sense also depending on what you want to achieve. Okay, so you may define have a loss like this, and you may define a loss like this. Okay, so it has certain form like what d minus log and y minus d, and yeah, isn't there is a mistake here? It should be a log here also. Okay, 1 minus d log of 1 minus y. Okay, so this is the cross entropy loss. As I said, there will be zoo of loss functions as well, and each loss function will come up with sometimes their own interesting features. Okay, so far both are differentiable. From optimizer point of view, both are differentiable. So both differentiable. So that's a good thing. You can go ahead with the gradient descent method and so on. Yeah, so in this case, derivative can be computed like this. Okay, so we can compute the derivative like this. Explicit derivative can be computed. Okay, so, and it will obviously depend on d, because d depends on 0 and 1. So if it is 0, then this term goes away, and then you only focus here, and then d is 1, then this term goes away, and you only focus here. So that way you will get this. Yeah, so if d is 0, only this term will be left, 1 minus d log of 1 minus y. So d is 0, then this will go away. So this will be the derivative of this. So derivative of log of 1 minus y is 1 by 1 minus y. Okay, the same thing happens here. D is 1, then only this term will remain. So minus log y, derivative of minus log y will be minus 1 by y. So derivatives can be computed. So these were the loss functions, and okay. So in some cases, obviously, the desired output can be one hot encoded, so that the ith position will denote some class. Okay, so output in this case will be a probability distribution. So in this case, so we can compute the cross entropy between one hot and the actual output as well, by using this kind of loss function. And in this case, the derivative will be like this, because this is just log of this. So for the cth component, the derivative will be given by yc. Okay. Okay. So Yeah, I will. Let me skip this, the level smoothing part. Okay, it does help in like gradient descent, but I will skip this level smoothing part. Okay, so yeah, so this is due to the level smoothing. Okay, so let us skip this for the moment. So there are reasons why it is helping in the gradient descent method. So let me skip this. So let me go to the main part. So what was the main part? So what we have seen so far is that neural networks can be deep. They may have many hidden layers. Challenge is to compute the gradient. Okay, and then we have many activation functions. We have loss functions, variety of loss functions. So and we can compute derivative for the loss functions, which we will need to compute the overall gradient. Okay, so in a neural network, what happens is the following. What will happen is that initially you will be given some sample and you are given some desired output. So initially you will not know what is the good weight anyway. So you will pass these samples. So let us say y0 according to our notation is our some sample x. So it will go through the network. It will follow the operations that we have already like made precise, that a sample x comes in, then they get a linear combination with respect to the weights. So this is the linear combination of the input sample with respect to the first layer weights. And then the activation happens with these functions fi. So these are the functions fi. Okay, and then yeah, so these are the functions fi, and then you do an activation again in the second layer, and that's when we compute the zj2. So these are the vectorized forms. It's just z2. Z2 contains all z1, z2 1, z2 2, and so on. Okay, so this is how we do a feed forward. So we keep doing this until we get the final output. Okay, so this is what we will do. Okay, and what will happen is that since the weights of your network are not very not optimal, your prediction is going to be bad. Okay, that is expected in the forward pass, and the output you are going to get will be very far from the desired output that you are expected, which is D. Okay, so but the reason why the reason why we will do a feed forward, and important thing is that we will store these values during the feed forward. Okay, why we store these values? Because these are the values that will help me when I'm computing the gradient, okay, of my loss function. And the gradient of the loss function will have to go backward, right? Because the chain rule, remember in the chain rule linear case, we have derivative with respect to this, we have derivative with respect to z, we have derivative with respect to y, we have derivative with respect to z, and so on. Okay, so these intermediate values that you have computed, z2, y2, all these are useful in computing the derivative. Okay, so we will see this. Okay, so in the forward pass, what happens is that I have this y0, and as I said, for the general so in the last layer case, okay, so this is, let us focus on the last layer case. So we have seen what happens up to here, and in the last n minus 1th output is here, and then so we will do the last step, right? So last step will so yn minus 1 was found after activating with respect to fn minus 1. So that's what we did, and this activation was applied on zn minus 1. So that's what we did here, and then once yn minus 1 was found, we took a linear combination here with respect to the weights of the nth layer. So these are the weights of the nth layer, and then we did a final activation. Okay, so it's the same thing is happening as before. It's just that we have identified what is the final output that we got. Okay. Okay, so so overall, what we can do is that we can make it into algorithm, and we know that the same thing happens recursive. Same thing happens as we go ahead from layer to layer. So we can actually apply a for loop, and the k is from 1 to n, and n is the number of layers. Okay, so n is the number of layers, so we can do that, and at each layer we are doing a linear combination of the previous output, linear combination with the weights of the current layer, and then we are doing the activation with the activation functions of that layer. Usually activation functions will be same. All fi to fn will be the same activation function. Usually you don't change activation function from. Okay, so and so that's how we will at k equals to n, we will get the final output y superscript n. Okay, so it's easy to now write this into an algorithm using this for loop. Okay, so in Python it's just a couple of lines. Okay, so this is the forward pass algorithm where you are given, you have the sample j, and then this is the for loop you are running. Okay, so the first for loop is for the number of layers. So this is the number of layers. And the second for loop is for the size of the kth layer. The size means the number of units. Okay, number of units or the neurons. Okay, neurons in the jth, in the kth, I mean, okay, in the kth layer. Okay, k is the so dk. So that is denoted by dk here. Okay, so I am at the kth layer. Okay, so this is the kth layer, and then the size of this is dk. Okay, so dk is the size of the kth layer. So the for loop will go also for all the neurons, right? So each neuron receives does a linear combination, right? So each neuron is doing a linear combination of the weights, okay, of the previous outputs, right? So these are the previous layer neurons, and all these are going here. Okay, so this weighted combination happened here, and then I move to the second neuron. So j equals to 2, and this was j equals to 1, and j equal to 2 also I will again have a linear combination. Okay, and then I go j equal to 2, j equal to 3, j equal to dk. Okay, so for all the neurons in there, and then I keep doing the activation also. So moment I have computed this guy, immediately I will go ahead and do the activation here. Okay, and similarly, a moment I have computed the linear combination here, I will do the activation and then get the output of the current layer, kth layer, as y superscript k from the jth unit. Okay, so this is the algorithm as such is very simple, as you can see, and the final output that you will report will be y superscript n. Okay, now comes the main part, that is that we need in the optimizer. It's to compute the gradient. Okay, so to compute the gradient, we did a feed forward, remember? So feed forward, what we did is that we did had these intermediate values, right? So we had these intermediate values when we did the feed forward, and we wonder why did we store these intermediate values, right? What was the use of that? Okay, so we have computed all these intermediate values in the forward computation. We must remember them because we will need them to compute the derivative. Okay, so let us see how. Okay, so computing the derivative, right? So and what derivative we compute? We compute derivative of the loss, right? And what was the derivative of the loss? In our case, it was denoted by dive function, right? So I mean, the small dive, you can think of these as the local losses for the samples, and then you can sum over the samples to get the bigger loss. It's similar to what we used before. So capital L and then the small l for the sample wise loss. Okay, so we want to compute the derivative of this loss function with respect to the weights, right? Because our model is a model on the weights. That's the only tunable parameter we have in hand, and we want to minimize our loss. So we will do step by step, right? So just like we did in a linear network, we will try to do this step by step using the chain rule. So first step is that our last variable was y to the n. So my loss function can be treated as a function of yn. Okay, so what I want is derivative of my divergence. Okay, the loss function with respect to the immediate variable. Okay, so is the derivative with respect to the final output of the network, which is denoted by yn. If I see divergence as a function of yn, but remember what is that we need in the gradient descent method? We need weights with derivative with respect to w, right? So these are the w's that are there. But to go there, we see it step by step. Okay. Then we compute the derivative with respect to the pre-activation affine combination Zn using the chain rule. Again, after that, we see that the dependency is on Zn. Okay, so then we need to compute the derivative with respect to Zn. Okay. Okay, so continuing on, we will compute the derivative of the loss with respect to Wn. Okay, so so if I had to stop here, right, then derivative of the loss with respect to yn and yn with respect to Zn. Okay, so if I have to d by, let us say, dzn, I have to compute of my loss function yd, then d by dyn, okay, of the divergence yd, and multiplied by dyn by dzn. If I have to compute this, then according to chain rule, first I see this as a function of yn, and then yn was obtained from Zn. Okay, so that is how. So this is how we will reach to w. Now you are supposed to compute w. So if it was a w, then you will do one more, right? So dzn by dw, something like that. Okay, so this is what we are trying to achieve. So let us see how. Yeah, so what we really want is this divergence of the loss with respect to w. So divergence of the loss with respect to w is the parameter. So this is w here. So w is what we need, and we need these intermediate values. Okay. So continuing on, we will compute this derivative with respect to the weights. Yeah, and then continue the chain rule to compute derivative of the loss with this and with respect to the outputs of the n-1 layer. Okay, so we keep going according to this arrow, right? So this arrow is telling us how to go step by step. Okay, so then we are at this step, we are computing derivative of the loss with respect to Zn-1 using these intermediate steps like I described in the previous slide. Okay, so this way I can keep going forward, and then these are the quantities that I really need, Wn-1. So this was the, so here are the weights Wn-1, and here are the weights Wn. Hence I can also compute this using the chain rule, and so on. Okay, so this goes on like this. Okay, so now let us get into, so we got the overall plan of how to do the how to compute the gradient, but that was like a very high level plan. Now let us see how the details of that, right? So first of all, if I want to compute the derivative with respect to the final output yi, so final output, I'm not putting y superscript n here. That will be computed. So I have to do it for all the y. So this will be for all the y, right? So derivative of the loss with respect to yin. So this is for all the y. So that's like the final yeah, output. Okay, so that's how I will get the derivative values. So this is now I now stands for ith unit of the final layer. Okay, so it's just same thing, is just that I am now computing it for all the I. So now next step was to compute this, right? Zn. So remember what I said, let us say Zn and the first component of Z. So this is Zn1, let us say, and this guy is Zn2, right? So I need to compute it with respect to both. Now derivative of the loss with respect to Zn1 will be derivative of the loss with respect to yn. Okay, so derivative of the loss, I mean this one. Okay, it's written in a flipped way. Okay, the first step is that this one. So you have to do derivative of the loss with respect to y1n. Okay, so you have to see the dependency, right? So my loss dependency is on this directly, which is yn1. Okay, so this is yn1 is here. Okay, and this is perhaps yn2. Okay, so my derivative will, because Zn is here, right? So the dependency is on yn. Okay, so this is coming from this branch, right? So I only need to look into y1 because Zn1 is not here. Okay, so it's enough that I follow this branch. Okay, so Z1n is here, so I see this as a function of y1n. So that's why I did a derivative of the loss with y1n, and then y1n had dependency on Zn1. So that's why finally I do y1n and then divided by derivative of Z1n. And since I only wanted derivative with Z1n, I just stop here. Okay, the chain is working in this way, in these notations. Okay, so this and then this. Okay, and this was the first component, right? Now what will be for the second one, right? So let us calculate this. So del div by del Z2n, right? So this will be, so let us write according to this notation, let us write the first derivative as the last. Okay, so this will be del div. Now what should I do? Z2n came from this branch, right? So it came via this branch because Z2n is lying here. So it came via y2n, not via y1n. So I will do y2n. So del y2n. Okay. Now y2n depends on Zn2, right? So then I will do the final y2n divided by del Z. Okay, so Z 2n. Okay. Okay, so you saw that you could also compute the derivative with respect to this and this. Okay, so yeah, so so what do we see from here? What we see from here is that this guy has been already computed. Okay, during the forward pass. Okay, so this guy has been already computed during the forward pass. Why do I say that? Why do I say that I already have this term, right? So we have to see how the loss functions looked like, right? So let us say we took a loss function that that looks like this. Is, let us say, the simple one that we have described before, y minus d squared. Okay. Okay, so this is a loss function that we defined here. Sorry, the 2 square is outside. Okay, so I need this, right? I need this. Okay, so if I need this, then so if I take a derivative of this, right? So let us say also half is there just to cancel out the 2. Then the derivative of this del div by del y will be y minus d only, right? Y minus d only, right? Because half 2 got cancelled. So isn't it that I know this? Yes, I know this because y is known from my previous forward pass, and d is also known because that's the given level. So this is known quantity actually. Okay, known quantity. So that quantity is known to me. That's why I say it is already computed. Okay, and that is why it is helping me, because I mean, in this output case, you will not appreciate why, because output anyway, you will say that I have to store, but even intermediate values, storing them will be useful because as you go along, those values will show up. And if you had stored those values, you can directly compute the derivative. Okay, so in this case, as a first step, since I have this final output anyway, so I will just, I know those values. I know final output value, D value. I get those values anywhere. Okay, the same thing I can do it for Y2. Okay, so this quantity is known to me. Now we wonder whether this quantity is known or not, right? Because our final aim is to go and compute the derivative with respect to the weights. So, but for the moment, like this is known to us. Okay. So, and let us focus here. Okay. So this is known already. So we forget about this now. Now let us focus here. What is this quantity, right? So this is del y1n by del z1n, right? So what was y1n, right? So y1n was what? Wasn't this fn, because it was obtained after activation of the z values, right? So y1n is this guy, right? So y1n is this guy, and this guy is obtained after activation of I mean I focus here, right? So let us focus here. So this output is yn1. This output is yn1. Okay, and this was obtained after I applied fn on zn1. So this was zn1, right? So y1n was obtained after I did fn of zn1, right? So if I want to do a derivative of this with respect to zn1, right? So d yn1 by derivative with respect to dzn1. So this will be just yeah. So derivative with respect to d by dzn1 of this guy. Okay. So this is f, which I can write it as f prime. Okay. So zn1. Okay. This is what is written here. So this is what is written here, right? Now the question is, what is this anyway, right? So that's the next question, Rao, because once we know this value as well now, right? Okay, so now we are wondering what is this, but this is a sigmoid, right? So sigmoid again, I mean sigmoid or whichever activation function you can think of, we assume that we know the derivative of those activation functions, and while we have the derivative of those activation functions, they will be some function of the derivative will also be some function of these z1n, and z1n values are known again because I have saved those values during forward pass. So I can store these values. So the derivative will be a function of z1n, and since z1n values are known to me, again I know this value. Okay, so this is how we can. So this z1n, that's what it's saying here. This was saved in the forward pass, right? And after derivative, this will be just some function of z1n. So wherever z1 is there, I just put that value because I have computed that during the forward pass. Okay, so so this is what we get eventually. This is something we knew beforehand, because depending on the loss, right, so this is something we know, and this is also something we can compute, and hence we can compute derivative of the loss with respect to z1n. Okay, so this is where we are now. Okay, and same thing applies for this guy also, derivative of the loss with respect to zn2. Okay, so it can be done as well. Okay, so in general, I can just put I here, and then for I equal to 1, I get this value. For I equal to 2, I get this value. Okay, so it's just we can put this in a loop, and then we can compute this guy. Okay, now let us look into the actual derivative that we are looking for. And what is the actual derivative we are looking for? We are looking for the derivative with respect to the weights, because that is what the gradient descent method is asking us to provide. Because the neural network is a function of weights, and the gradient method is trying to optimize the neural network values for the weights with respect to weights. Any other weight derivative are just intermediate values that is helping us, but what we really want is derivative with respect to weight. So now let us again start from here and see how we can arrive at the weight, right? So let us say this weight is wn11. Okay, let us say indicated by some blue arrow here. Okay. Okay, so I want to compute the derivative of the loss with respect to the weights. So what are the ways I can come here, right? So I know so far I have discussed that I can compute the weight derivative of the loss with respect to z. That's what we showed in the previous slide. Derivative of the loss with respect to z. I know how to come here, although I know that I do it in a two-step. but I will forget those intermediate steps for the moment. I know that I can get derivative loss with respect to Z, and then Z is a function of the weights, or in particular this, if we focus on this blue weight, let us say this weight. Okay, so now the dependencies are divergence of YD depending on Zn, and Zn depending on Wn11. Okay. So if I want to compute derivative of the loss with respect to W, then I will go in a two-step process like this, and that is what is done here. So derivative of the loss with respect to Z1n. Okay, so because so Z1n, so derivative of the loss with respect to let us say this guy Z1n. I think according to our notation, this seems to be a bad idea to take this because this is pointing here, right? So let me choose some W11 as this guy. Okay, so this is my W11n, and this W11n has an influence on Zn1. Okay, so it has an influence on Zn1, right? So that is how we are tracking the dependency. So loss. So where is W11 in which branch, right? So this is my loss. If I follow this branch and I arrive at Zn1, and Zn1 actually use the Wn11 value. Okay, because this guy did not use that value. This guy used W12 value, right? This guy was having W11 value. That's why I will never follow this branch. I have nothing to do with Z12. Okay, so the weight W11 is here, and that has dependency only via this way. Okay, so it goes like this, it goes like this, it goes like this, and it goes like this. Okay, that is why I have nothing to do with this guy here. So I will never bother to do anything with W. I will never do anything with Zn2. Okay, so this is what we have. So this is how the chain will go in this direction. So this is what we have done. Loss with respect to Z1n, because that was the only one that was directly dependent on W11, and after that Zn1 by del W11. Okay, so this is where we believe is W11. So we use the chain rule, and then we found this quantity, right? And the same idea now will hold for W12. Okay, so W11 is here. Okay, and then we will also have like W21. Okay, and then W31, W41. Okay, and then W12, W22. Okay, W32 and W42, something like that. Okay, so this way we can track the branch, and then we can compute the required derivative. Now the question is, how do we arrive at this derivative, right? Now let us look at this quantity, right? This is something we already computed. Okay, this is the whole previous slides were focused on computing this. So this is already known, right? And now our focus should be here. Like what could be this guy? So this is something we already computed, right? So that's what I'm again pointing out here. This is already computed in the previous slides. And our focus should be here now. So let us see what is there. So what we claim is that del Z1 by del W11 is just going to be Y1 n minus 1. Why is the case? Because remember, Z1 n was nothing but the linear combination of the outputs of the previous layer, right? So Z1n, which is according to our notation, is this guy, right? So Z1n used was the output computed after we did a linear combination of. So let me write down fully, because here many things are hidden in other terms, right? So Z1n is Z1n, this guy, Z1n is a linear combination of the weights W11, W21, right? So let us write that. So W11 Y1 n minus 1 plus W21 n Y2 n minus 1 plus plus W n1 n okay, and yn n minus 1. Okay, so yeah, I hope we don't get confused with this 2n, because there is no, I mean, there is no reason that the number of units has to be n only, but it doesn't matter. Okay, I could have chosen something m also, it doesn't matter. Okay, so so here also, like, I could have chosen m also. Okay, so this is the linear combination, right? Now, and then I want to compute the derivative with respect to W11. So I have to locate where is W11, right? Because that will be the term that will matter for us. So that is why this is pointed here explicitly. And other terms does not have any W11, so they will be treated like a constant. So if I take a derivative, they will go away. Okay, so hence this implies that dZn1 by dW11n will be only this guy. I mean only y1 n minus 1. Others will go to 0 because they are constant, right? So that's how we get this value. And this is also known, right? That is known during forward pass. That is why all these intermediate values are stored, because they are used in computing the gradients. So this is computed in the forward pass. So that's also is known to us. And yeah, so, and we can generalize this. Okay, so we can generalize this by you doing ij term. So we can generalize this computation for all the weights, all the blue curves that we have here are computed in the same way. It's just that you have to choose a proper I and j. That's it. And yeah, for the bias term, you can define these y0 n minus 1 to be just 1. Okay, because the bias terms goes with just the weights. Can be denoted like this. Okay, so so for the weights we did. Okay, and for the first layer, now so now we are going further ahead. Okay, in our first okay, while going backward, we have computed the weights, all the weights, right? Now we have to go here, and these were the weights, nth layer weights. So now we have to compute the gradient with respect to n minus 1th layer weight. So we have to go via this step again. Okay, so what are the challenges we have now? Now the another intermediate variable that is left is yn minus 1, right? Now I need to know how to compute derivative with yn minus 1 now, right? Yn minus 1. Okay, so what do we do here? Yn minus 1 has dependencies on Zn, and then yn minus 1 is also used here in Zn2 also. Okay, so this is a little bit interesting, because what was happening so far is that if I am computing the Zn values, right, then the branches were coming like this, right? So branches were coming like this. Okay, and then I had one output value and so on. But in this case, if you see yn, if you see yn minus 1, the yn minus 1 is depending on both Zn1 and Zn2. Okay, so it's depending both on Zn1 and Zn2. So that is why now we have to sum over Zn1 and Zn2. Okay, if we want to compute the derivative with respect to y1, then we need to sum over this, because the dependency here is now both ways now. because y1 minus 1 was also used here. Okay, so now this branch is also important. Both the branch are important. Okay, so let me. Okay, so the first branch is this way, but then yn minus 1 was also fed here. Okay, so this branch will also be used now in the chain rule. So this is what we have to do here. So now we have to add it. So to do that, we have to do del diff by del yn, I mean del z1. Okay, so since we have these values already, since we have computed these values. Okay, I don't know what is happening today. It's just get stuck. Okay, so divergence of the loss with respect to Zn1 and Zn1 with respect to yn minus 1, 1. Similarly, you have to follow this branch also. Now divergence of the loss with respect to Zn2 and Zn2 with respect to yn minus 1, 1. Okay, that is why now you have a sum also. Okay, that is why we have a sum. So what is to remember from calculus is like if you have like this, then you have to sum over this. Okay, and if you have like this, to this, you can just follow this way. Okay, but then if this value was used in both way, then both are influencing these values. So while doing the derivative, I have to sum over these two. Okay, so that is the reason why you have a sum here. Okay, so we already know these values. The Zn1 and Zn2, these values are known to us. So and then these values also are known to us because Zjn are a linear combination like this, and then we have to compute the derivative with respect to y1 n minus 1. So we will just focus on the term that has yn minus 1. Okay, so if we take the derivative with respect to that, what is left is the weights w1j n minus 1. Okay, so that's what is found here. Okay, so these now values are also computed, so we can do it for all the I. Okay, so just we did it for one, but we can do it for in general for I. Okay. Okay, so this way now we can from here onward you will see that it's recursive pattern. This y part was tricky a little bit because there was a branching out here, but we know now how to compute this y. Now from here, just like yn to zn you went, now you have to go yn minus 1 to zn minus 1. That is why the formula looks exactly the same, just the n changes to n minus 1 here. Okay, the same way we can compute these values, and then yeah, bias all the time we keep taking 1. Okay, so and yeah, so this way now we can arrive at the n minus 1 level weights, and we can compute in the same way as we did it for n layer weights. Okay, so again we can apply the same, and then we go ahead and we do n minus 2 again. N minus 2, there is a branching out, again we will have a sum, and so on, and again we can compute the derivative with respect to n minus 2 zi, and then we compute the derivative with respect to y11 and then z11 and so on, and then finally we arrive at the last layer weights, which are these guys, and they look like as before. Okay, so they also, so all these values yi, zi, all those values that are needed in the intermediate values, they are all computed during the forward pass, so they are all stored, so they can be used. So this is the back, this is so-called back propagation. So back propagation is nothing but the chain rule to compute the derivatives. And the reason why it's called back propagation is that we go backwards. Okay, in the neural network we have a concept of forward pass, and then during back propagation we actually compute the gradient. In other words, we tune the network. Tuning the network here means that we tune the weights. Okay, we decrease weights such that the loss is minimized via gradient descent method. So this is all that we have. So this is the loop for the back propagation. Okay, so we just have to like make sure. So the loop is going backward, obviously. So n-1 to 0, and then layer width. So what was the layer width or the dk? If you the previous notation was dk for us. So number of units neurons in the current layer, kth layer, and then we just substitute these values, and then finally what we really want are the weight values. And this is what your backprop algorithm should output, the derivative of the loss with respect to the weights. And this is the one that will be used in the gradient descent. Okay, so this is the algorithm that we have. Okay, final algorithm that we have to compute the gradient descent. So there could be some special cases. For example, there could be cases where you have, for instance, so what we have assumed so far is that computation of the output of one neuron doesn't directly affect the computation of the other neurons in the same layer. And outputs of the neuron only combine through weighted additions. Activations are always differentiable and so on. So there are a few assumptions we have made. And there are cases where we have vector activations. So far what we have assumed is that activation functions are scalar activation functions like sigmoid, but we could also have a vector activation function. Okay, so in that case we have to change few things in the derivative computations, right? So for instance here, if you see, if you take a linear combinations and then it affects only one yk, okay, but if we do a vector activation, then one zk is influencing multiple outputs. Okay, so there are dependencies like this, there are dependencies like this, and so on. So in this case, when you are computing derivative from yk to zk, and since the branching is like this, again you have to consider the sum in the derivatives. Okay, so you have to consider sum in those cases when you have vector. So the yk is obtained after vector activation, right? So in that case, if I take a derivative of my loss with respect to zk, then I have to sum over all these branches. Okay, so these are the minor changes that one has to do. Yeah, so this is what I said. If I have to compute the derivative with respect to now zi, data is influencing multiple outputs, I have to have the sum now. Okay, so these are the changes one has to do. And final algorithm can look like this. Okay. Gradient descent. Okay, and you can say that, yeah, so what did we do overall? The training of the network will look like, first you do the forward pass. Okay, and in the forward pass you store all the intermediate values that you are going to need, and then you compute the derivative for loss with respect to the weights. And of course, while computing this, you will use up all those intermediate values, and then you will take a cumulative gradient, and then you will do the gradient update here. Okay, so these are just a algorithmic form of what we have discussed so far. So main thing here was to compute the derivative of the loss, okay, with respect to the weights. And once I have that, then I can make a gradient of the loss like this, and then I can just update it for update my weights. Okay, so this was the, and then yeah, we can write, we can formulate things in a vector form. We can use a vectorized notations like this, and yeah, in vectorized form, yeah, so in vectorized form the forward pass looks like this. So if you can vectorize things like this, so you accumulate the weights of the kth layer as a matrix, then it's very simple operations now, and even your activation functions have been now vectorized, so it can do activations simultaneously for multiple inputs of ZK. So a network is indeed a nested functions, and error for any x is also a nested function. So if you look at the loss function like I described before, it is a nested function like this. And okay, so I'm going to skip this because this is for the vector activation right now. Okay, I will skip this for the moment. Okay, so what this is trying to say is like if your activation functions are like vector activation means that the output of the activation function is a vector. Then in that case, if you want to compute the derivative of the activation function, remember we needed f prime z like that, right? But now since f prime is a vector activation function, the derivative will be a matrix. Okay, so how it will look like, this is just the details of that. Okay, so so these are just details. So derivative of y with respect to z will be given by this matrix of the derivative. But if it happened to be a pointwise, then it would be a diagonal matrix, obviously. So that's what is shown here. So this is just a diagonal matrix in the usual case when you have activation functions which are scalar outputs. So this is just trying to like so in that case, if I consider the ZY matrix, they individually have to take the derivative. Okay, so this is so what this is trying to say is like in general, I can also write a vector algorithm. So this is the yeah, so this is like the forward pass here, and then I can also compute derivative using matrices and so on. Okay, so you can have a look into this. It's not a big deal. So in a vectorized notation, I will use the concepts of Jacobian now, okay, because of the vector activation functions and so on. So if I now just go directly to the algorithm, so this is the same algorithm that we discussed now in a vectorized form. Yeah, so this is like the backward pass, but with a vectorized form. Okay, and now we are also generalizing it because we are allowing also the vector activation function. So in that case, we will have a Jacobian and so on. Okay, so this is the whole neural network algorithm, including for the vector activations. Okay, so I think with this I can stop for the neural network part. So we have discussed this third model, which is neural network model. The challenge is computing the gradient, and we have seen how to compute the gradient using the chain rule and so on. I think with this I can stop with this, and then in the next class we will try to learn some more optimization solvers. So we will discuss some second order methods and so on. Okay, so I think with this I will stop here. Okay, if you have doubts, then you can ask question. I know that some parts I have skipped a bit. Those things are not that important for your exams. Okay, so I have skipped a little bit just to cover things. Okay, then, so I can stop, and if you have questions, you can ask.
Sir, the sigmoid function, can it be used for multi-class also?
Yeah, you will use the softmax actually. Not softmax is the vector activation functions, not the sigmoid. Okay, so because we need to do the scaling, proper scaling also, because now you have a multiple class. So we have discussed. Let us see the. I think it's before softmax. Softmax is before this one. Yeah, so you will see that the softmax is defined in this way. So this is the vector activation function. If you want to see an example for this, this is how one would do. Not the usual softmax, but not the sigmoid, but this way. Okay. Yes.
Okay.
Because yeah, some kind of scaling is also needed. So output from the other ones also has to be scaled out. So softmax is appropriate in that case. Okay, so it seems there are no more, so I should stop the recording first.